Welcome to the Here's a Summer of Programming Languages. Have you ever asked yourself, am I using a suitable programming language for this task? Then this collection of introductions to programming languages used in research software engineering has something for you.
Hello everybody and welcome to another HiRSE Summer of Programming Languages seminar. My name is Ivo Kabadshow and I work at the JSC in the HTML concurrency and parallelism. And we develop libraries for our HPC machines here. The topic of today's talk will be C++. And since we have to celebrate a birthday, C++ is 40 years old, I subtitled this talk Midlife Crisis at 40, and we basically take a look if C++ is a language that you want to use in your projects. When talking about programming languages, I usually start with a quote, and today I have a quote from the creator of C++, Bjarne, and the quote basically goes, there are only two kinds of languages, the ones people complain about and the ones nobody uses. And if you ever have been to an online forum, you probably agree that there's a lot of discussions going on, what's the best language for this and that. And I hope I can shed some light on this today. Okay, part one, introduction. When we talk about programming languages, usually people discuss about features a programming language has over another and how easy a feature is achievable. I'll try to change this a little bit and present it in a different way and basically start from the requirements your software needs. So in this slide, I basically highlighted the critical wall time you have in your, or you could have in your software, and want to basically show you that not all software is created the same and that different software has critical wall time. On the left, you basically see the hardware wall time, where you have the CPU cycle in less than a nanosecond because it clocks up to a few gigahertz, and you have your network latency in the realm of a few microseconds. If you look at the software side, on the right side of the slide, you can basically see two applications I just picked, which is deep learning and astrophysics, and the critical wall time for that is in the realm of minutes and hours. But you might also have other applications, like molecular dynamics in the middle, where you have a critical wall time in the range of milliseconds. It doesn't mean that your application runs only milliseconds, it just means that, especially for MD, since we have so many time steps, we have to achieve each time step, which represents the critical wall time, should be done in a millisecond. The same is true if you work in industry, for example, in game development or high-frequency trading. In game development, obviously, you want to be able to present the next frame in your video game, and if you have 120 Hertz, you're also in the range of milliseconds for your critical wall time. So basically, the application you're writing defines a little bit what you require. And you could ask yourself the question, where's your application on that timeline? If you're more performance critical, you will be more to the left towards the hardware. And if you're not that performance critical, you're probably a bit more to the right. And this can be one way to decide which language is good for you or which language you require. Another point of view is looking at the software stack. And if we start at the very bottom, usually we start with hardware, the physical components. There's no programming going on, but right on the next step, if you're writing, for example, some firmware, some system-specific software, you probably need a programming language that helps you with that. If we go up the software stack, the next layer would be your operating system, the kernel, or the hypervisor. And on this level, you basically have to deal with all kinds of memory management, block device management, interrupt handling, and probably have to support a lot of different hardware layers. If we go another level up in the software stack, then the application program interface follows. At this point, you basically have to provide the virtual memory access, the interfaces for applications towards the operating system. Even higher in the hierarchy, you can write also libraries that can be linked at runtime. For example, if you think about the FFTW or other libraries that can be used for multiple codes. So basically you have a library that is capable of providing a certain feature, in this case a Fourier transform, and different codes can use it right away. Even one step higher is your application that usually comes from a domain science, so it could be an application from physics or could be an application from biology. On top of that, you would set the user interface, basically where the user can set up the dials for the application necessary. And if you go to the highest level of the software stack, I would define the user-defined workflows at this point. So basically all the automation you could do to orchestrate your applications, and how to deal with output values, how to deal with input values, how to combine different applications. And if you ask yourself, well, what about C++ and which level of the software stack it's often used or useful to apply, I would say the lower levels of the stack, almost to the top, is a good application area for a good application candidate for C++. One thing where C++ shines is basically if your application is performance critical. So therefore we will not use it in user interfaces or the user-defined workflows, but everything around the runtime, libraries, or applications that are performance critical should use C++. Another thing that could be a requirement where C++ shines is portability. For example, if you not only want to support one machine, but multiple machines, so multiple architectures like x86 or ARM or an RISC-V architecture. You could also look at from a different perspective. There's a ISO norm for software quality, and it consists out of 9 different groups: functional suitability, compatibility, reliability, performance and efficiency, interaction capability, security, safety, maintainability, and flexibility. I highlighted 3 of these 9 groups that probably are important for you as an RSE. And if we take a deeper look at what these things mean, performance efficiency basically means like how efficient are you using your resources. This could be time, this could be throughput, this could be capacity. Maintainability obviously describes how well your code after you've written it can be modified by somebody who's capable to maintain it. And flexibility describes the possibility of porting the code to be able to run that code on a different set of machines. So if you have, for example, a different hardware, how easy is it, how flexible to run it on a different machine? If you look at these software quality groups, I'll just take 5 out of these 9 that are probably relevant for you in your application. And let's start with maintainability. Obviously, we want to be capable of maintaining the code after it is written and extended to a certain amount. And if you define a radar chart like this, and you basically have like marks from 1 to 5, and 5 would be the best and 1 would be the worst, I would say C++ is somewhere in the middle. Regarding maintainability, there's other languages that are obviously a bit easier to read, but there's also other languages where this is a bit harder, so I would put it in the middle. The next point where C++ really shines is performance efficiency. So if you pick any architecture you can think of, the goal of C++ really is to get you the most out of the performance the hardware provides. So I would give it the 5 points here. Another thing that's also lately in the discussion is safety. So you can think of memory safety, for example, that's available in Rust. C++ doesn't have a thing like this yet. So therefore I would mark it as a 2. And the interaction capability is basically, so how hard is it to learn what the code describes. I would give it a good middle 3 points. And flexibility, basically how capable is C++ to run on different platform, I also would give it a full 5. And then you get like a radar chart like you can see here. And now you as a upcoming software developer have to decide, is flexibility, so the possibility to run on multiple machines, or is performance efficiency something you need in your application? And if you do, then C++ here is a very good fit. If both of these are not top priority, then obviously you don't have to choose the language, and you can stick with any language where other fields like safety or maintainability are higher in the chart fit better. Another angle that you have to take into account is modern CPUs. Almost every CPU you can buy today exhibits some parallelism, and if we look closer at Flint's processor organization diagram, you can see that there's like 4 different schemes you can group your parallelism into single instruction, single data. Despite the fact that it says single instruction, single data, you still would have instruction level parallelism on this side. So this is something you can optimize for. Then you have single instruction, multiple data. In the middle here, basically all the vector instruction, AVX, SSE, SVE falls into that category. And at the right part of this diagram, you have multiple instruction, multiple data, and there you have your intranode parallelism and your internode parallelism. And basically 90% of this diagram, so everything except the distributed memory at the end, you already have in your laptop. So if you want to get the full performance out of your CPU, you have to program at least 3 paradigms: instruction level parallelism, vectorization, and some threading in order to get the performance out. This, however, is only the viewpoint from today's CPUs. You could also go a bit beyond that and ask yourself, like, okay, we also have GPUs, and we can also use that for our calculations. And if you ask yourself a question, if you look at the top 3 supercomputers in the world, how is the ratio between the CPUs and GPUs? And the disturbing part is it doesn't look close like that. It looks more like that. So basically, all the performance of today's supercomputers, or even a single node inside that supercomputer, does come almost purely from the GPU. So you can see this is the top 3 supercomputers in the world today. And top 3 Aurora has 84% of the performance coming from the GPU. So even if you do all of that, as I just explained before, for a CPU, you're only working in this blue region down here, and your GPU is idle, and you didn't do anything. And it's getting even worse if you go to number 1, El Capitan, where 97% of the performance does come from the GPU. Problem with that, it does get even worse if you go to a lower precision. So this is FP64, so double precision. If you go to float or even half precision, these numbers go close to 99% even. Also something you have to keep in mind when choosing a programming language. In a part 2, I want to tell you basically our user story, how we came to C++ and how we started. And I hope this helps you decide if you have a similar story or see that it could work for you. So let's dive in. So basically our story is starting with a Fortran code back in the days in 2001. We had a very initial version and only a single person, a single developer working with it. And back in the days, everything was simple. There wasn't that much parallelism around. There was no GPU around. So Fortran was a good choice because you could easily map out all the math into your Fortran code. And the idea was basically to write a library that provides a fast multiple method for MD. In 2004, however, the team did grow a little bit. So now 2 people were working on the FMM, and over the years, a lot of algorithmic extensions has been added to the codes, and we ended up with around 100,000 lines of code at this stage, and we had now 2 developers. Things got more complicated, so we decided in 2010 to introduce some version control. Back in the days it was SVN, and we provided the library into another library, the SCAFACOS library. The problem at this point was it wasn't simple to vectorize the code, so basically Fortran had no SIMD support at this time, and the compiler also could not help us auto-vectorizing the code. Another thing that came up at the time was internet parallelism. So basically, the processors now started to have multiple cores. And in a very early stage, people just used MPI ranks for each of these cores. But at this point, this did not work anymore, and one had to think about another layer of parallelism, basically some threading inside the core. So finally, in 2013, we decided to move over and port the code to C++. Back in the day, it was the standard C++11, and we also changed from SVN to Git, had our nice little make system, and now even got an extra developer in the group. So all the tooling around is also important if you work in a group, and now it was much more easy to attract people to deal with the code, because at that time, not many people did know so much Fortran, and it was really hard to get the performance out. So C++ helped us at this point to increase the support for different hardware and get even more performance out of it. In 2015, we decided to split the FMM library into 3 separate libraries. So one more generic library, a C++ template library that provides all the machinery that can be reused in our taskification library. And we also added basically a SIMD layer at that point. The idea was to reduce the number of lines of code even more per library and try to separate concerns. So tasks should have nothing to do with the FMM itself, and the SIMD should be a separate layer as well. So it's not tailored to the FMM because we can use it elsewhere as well. So the idea was to just split that apart. And with C++, this was possible to do. In 2020, we started to change the build system to CMake, which allowed us then to use the continuous integration tool a little bit better. And in the next year, we modularized the code even a bit more and increased the standard from C++11 to C++17. The reason for that was basically if you do a lot of template metaprogramming, in the old standard was kind of cumbersome and let's say boilerplated code we want to get rid of, and in C++17 we could reduce the lines of code even more without losing any of the features. Finally, in 2024, we tried to implement everything also on a GPU. So therefore, we moved to CUDA and C++20. And this is basically important if you want to do anything on a GPU, and since C++ and GPUs work together so nicely, and you could use different libraries like CUDA or HIP or Circle, this was the first point of switching over to a GPU. If you would ask me at this point, would I make the same decision to move to C++ again? The answer still would be yes. And the reason for that mainly is GPU support within C++. This works really great, and I agree that probably it's a bit more work to get the performance out, but at least you have the possibility to get your performance from the code if you try. One example I can show you here, if you define your algorithm in a certain way, basically I call this formula-aware memory layout, basically the same way it is written in a math paper. You don't have to understand the details. We basically have our input here, which is a multiple expansion on the right, then an operator that rotates this expansion, and we get a rotated expansion at the output. And you just see basically the memory layout. You don't need to understand what the math does. And the visualization you can see here is basically how you would write it directly from the formula you get from the paper. And unfortunately, because of this triangular structure and this pyramidal structure here, the compiler cannot auto-vectorize. So you lose some performance because vectorization is not possible, and the compiler will just give up. The advantage with C++ we had now, since we have full control about our memory, we can reshuffle the data and basically order our data regarding a certain SIMD width. So if we would have, for example, a SIMD width of 4, we would just combine 4 of these multiples together and have one operation with all of these 4 to get these 4 out here. Obviously, that is an explicit memory layout, but the compiler now is capable of doing the vectorization, and we can even do it in variable width, because how many multiples we stack in that dimension is basically a parameter we can set in the code. One question people usually ask is like, okay, now you have the complexity in your application, but we have a separate layer for that where we hide basically the vectorization layer, and the code itself looks exactly as the classical code you have seen before, where you have a single input, which is not just a set of inputs, a single operator, and a single output, which now is just a set of outputs. Okay. As a third part, I want to talk a little bit about the C++ ecosystem. So what can you expect if you use C++? And first of all, I want to talk a little bit about the programming language itself. So C++, as many other languages, not a single paradigm programming language. So here you can basically see a table of different features: concurrency, constraint-driven, data flow-driven, functional programming, generic programming. And I did put a list of some programming languages in this table, and you can basically see what these programming languages support. It still does not mean that the quality of support is the same for all the programming languages, and you shouldn't base your decision on how many bullet points you basically check, but it gives you a hint which programming paradigm is supported or is not supported. And if you are capable of speaking all of them, that's even better. But yeah, that's what basically C++ can give you. And compared to the other programming languages, it's a really multi-paradigm programming language you can use for almost everything. Another thing we can look at is the C++ compiler support. What you can see in this table is that there's 9 different compilers available to compile your code into a binary, which is good, because obviously competition makes all of them better and makes sure that you get high quality code. And what you can see in the first column of this table is basically the C++ 20 standard and how many features of that standard each compiler supports. So for example, GCC supports all 69 out of 69 features. Clang is close, with only one missing, and you can basically see that all of the compilers on this list support the C++ 20 standards to a majority. If you look to the next standard, C++ 23, you can already see the support goes down a little bit, and not all compilers support everything, but at least our top 2 compilers, GCC and Clang, allow you to implement basically almost everything from C++ 23. And even the upcoming and not finalized C++ 26 standard already is supported with a good 2/3 with Clang and GCC. And this is really helpful if you have a language that early adopts the new standard, and you can play around and figure out if a new feature is something you want to use in your code, because the compiler supported very early. Another thing when talking about C++, people are usually under the impression that not much happened. And if we look at the timeline of the C++ standards back from the 80s, you can see that it took quite a long time to developed the C++ 98 standard, almost like 10 years. And then we gained a little bit of speed with C++ 11. So you basically can see that some libraries have been developed, some special function, and yeah, it took a few years to develop that standard. But at some point, if we look at the time after 2010, you can see that we now have like a 3-year period of updates to the standard. So we have C++ 14, 17, 20, and a lot of things developed in parallel that will go into the new language. So basically, if I come back to my initial claim, is there a midlife crisis? You can clearly see that C++ has no midlife crisis. The opposite is true. In the last years, development gained a lot of speed, and a lot of features that people requested are coming in the latest standards. And even for the upcoming years, you can see there's the latest one, C++ 23, upcoming 26, and even 29 is already marked. And let's just wait how many features are coming into these versions of C++. If you're into the popularity index TIOBE, you can also take a look how C++ developed over the years. So back when it was created, C++ hit the index on rank 10, and then it climbed up, almost staying all the time in the top 5. And the funny thing is, today in 2025, we are second to Python, and I think the only reason Python is on number 1 is because of all the AI frameworks. So second in place is C++. So if you want a language that is very popular, C++ is also a good choice for you. Another thing that's really important is how much support, how much libraries are available for C++. So the good thing is there's like a bunch of different categories you can think of, and there's a lot of libraries in each category available. So there's no real need to reinvent the wheel. You could just start with your program and pick a library that's suited for your specific problem and just use it. And since this has been tested in real world, this is really good because you have like a proven library that works. Also, when you go back to all the parallelism we have in hardware and all the concurrency we have to provide in our libraries, you have support with Cocos and HPX that helps you out with parallelizing your code. When we are talking about parallelism, another thing to keep in mind is GPUs, as we mentioned earlier. One thing that really works well, all the big vendors like NVIDIA, AMD, or Intel basically provide libraries that have been tuned very well to their architecture, so you don't have to rewrite your BLAS routines or your fast Fourier transform or almost anything else that can be reused by others. And all the companies basically provide you a library that you can use right away. Most of the time, the library itself is not open source, but you can just use it as is, and you don't have to worry about getting the performance from these machines. The good thing about these libraries is that C++ is the main target. So there exist other bindings to other languages, but since C++ is the main target, you will get updates really quickly when choosing C++. Another thing that I find really important is the exchange with others about ideas in the language or how to do things in a certain language. And C++ is well and alive, and there's a bunch of conferences where you can go to. The biggest one, obviously, is CPPCon in the US, but there's a few more conferences all around the world that basically happen in a yearly manner, and you can go there in person, or in some conference even join online and discuss with the people the new trends and updates to C++. In the last part of the talk, I want to go into some details about the features of modern C++ I really like today and I would like to see in the future. On the left side, you can see what you can already do in C++ today. One thing that I really like is generic programming, in a sense that you could, for example, define a general routine that can handle multiple data types, so you don't have to rewrite your code for float, for double, for half precision. You write a generic routine, and the generic routine is then instantiated with the specific type that you need at some point in the program. Another thing that really comes in handy is modules. So up until now, you basically had your classical include files. With modules, this allows you a bit more flexibility. Third on the list is compile time evaluation. Basically, if some routines can be, if some function can be evaluated at compile time, you can enforce the compiler to do that. So especially for performance, this helps you quite a bit. And one more thing that is important is constraints and concepts. So basically requirements and set of requirements that you can provide for your template parameters. Last on the list is coroutine, which allows you now in C++ to have like suspendable and resumable routines. In the future, planned for C++ 26 and beyond, they think about a model for asynchronous computing. So basically, language support for really doing concurrent computing and in an asynchronous way, obviously. So you can basically offload computation to a device like GPU or to a different core and keep the workflow within the C++ program. Another thing that probably will be interesting is static reflection that allows you to basically inspect the code at compile time. One thing we are usually doing by hand and which now can get support by the language is SIMD. It would be really great. Another thing that basically allows you to give some pre and post conditions for your function would be contracts. And last but not least, the committee is also thinking about providing a generic unit system like SI units also as part of C++ itself. I'll have to name also a very extensive online reference, which is just CPP reference. So everything you could ever ask about how a feature works, how an example looks like, or even sometimes how it's implemented, just go to a CPP reference and it will show you all the different features and possibility of C++. So to conclude, when we talk about HiRSE and C++, I made two sections. At one we have the cons and on the other one we have the pros. Let's start with the cons. One downside for C++ certainly is the steep learning curve. So it's not like trivial to learn C++. And one main problem with that is that there's a lot of outdated guidelines available online. So it's not simple all the time to find the best way to do it with modern C++. Sometimes you find really old resources, and this obviously is something you wouldn't or you shouldn't do. One thing that is good to run old code on new hardware, but is bad if you start developing from scratch, is backwards compatibility, because technically it's still unsafe. You could still write unsafe code by just using raw pointers. So if you don't adhere to the new standard and just use the outdated guidelines, then basically that's a thing you shouldn't do. The pros, however, are also there. What I really like about C++ is like the ecosystem itself is really mature. So all the tools and all the libraries are available. You can play around, and most of the things you can think of have been written, and you can try it yourself and even extend if you want. Another thing that I really like about C++, basically, it once compiled, it runs everywhere. So there will be C++ compiler for any CPU on the planet. And this also extends to GPU, and this is really a stronghold of C++, I would say. And if you're really into the performance of your code, or you require high performance, the full memory control is really neat and helpful in order to get this performance. One thing that I really like is the zero overhead principle. So basically you don't pay for anything that you don't use, except for runtime type information and exceptions, but you could disable it for the compiler. So basically you don't even pay for that. But if you want these features, then you obviously have to pay. And another good thing is that modern C++ guidelines are now available in an increasing number, and this helps you quite a bit to modernize your code. Last but not least, you should not put too much effort in finding the right programming language for your project, and at some point just start coding. And as you can see from the chart, there's no such thing as good code, and this shows the usual way how a project works. You can either choose to do it right or do it fast, and even if you do it right and code well, there usually are two possibilities. You're either not done because you extend the code, as in our case, or if you're done, the requirements change and then you start all over. So ideally, you just start with your project, and over time you can figure out if the language is right for you, and if you need to adapt, you then just do that. With that, I'd like to thank you and hope you learned something, and see you in the next video. Bye-bye.
Thank you for watching this introduction. Please check out the slides on Zenodo, linked below, and see you next time.